In today's video, we're going to work on polynomials, rational functions, and end behavior. So at the end of this lesson, you should be able to identify which functions are polynomial functions and to what degree, and then identify which graphs are not polynomial functions. So that's part one. In part two of this video, you're going to identify the end behavior of a graph, find the zeros and multiplicity of a function. So there's a couple things we have to talk about. So first of all, polynomial functions refers to functions that are smooth and continuous. So to better define what smooth and continuous are, smooth is going to refer to graphs that have no sharp graphs, just rounded curves. And continuous means that we can draw the graph without lifting our pencil, or the graph will not have any breaks. Just a heads up, square roots are not continuous. So let's look at these examples and identify which functions are polynomial functions and to what degree. So in example 1, 5x squared plus 6x cubed is a function which has a degree of 3. Now this is a function because all of your x values are on the numerator. It's a degree 3 because your highest exponent is 3. Looking at example 2, notice we do have a fraction right here, but because your fraction has the 5 on the denominator and the x on the numerator, this is a function of degree 5. Now, even though you have that 7, we're only looking at the degree of the highest exponent. In example 3, you'll notice here that we have a fraction. And in this fraction, we have x's, or variables, on the numerator and denominator. Because we have an x on the denominator, this function does not count as a polynomial function. So, not a polynomial function because it has that 3 on the bottom. For example 4, like we mentioned in the previous slide, this is not a polynomial function because it has a square root. That means this graph will have sharp turns and you won't be able, or it's not continuous. So please make sure you include this in your notes. What type of functions are not polynomial functions? So in summary, any function that does not have an x on the denominator is automatically a polynomial function so long as that x is not in a square root. So let's look at what those graphs look like. Now looking at the graph in example 1, you'll see that this is continuous because it goes on forever, and you'll notice that none of the curves are sharp turns. So this is a polynomial function in example 1. If you look at the graph, it's the same exact example from the previous page. Example 2, you'll notice that it is continuous and does not have any sharp curves or sharp turns. Therefore, it is a function, which matches example 2. Example 3, you'll notice that there's a break in the graph. There's this area right here where the graph should have been connected, but it's not. And because of that, it is not a polynomial function, which matches example 3 of the previous page. And last but not least, example 4. In this example, you'll see that it starts over here at 5, comes up, and then comes back down. Notice it's not continuous because it's not going on forever on both sides. It stopped over at the top. So that is not a polynomial function, and it has a square root. So what types of graphs are not polynomial functions? These are the graphs that have sharp curves or have breaks in the graph, or are not continuous. Now, really keep in mind and take note of the examples from this page and the previous page on what was a polynomial function and what was not. So now it's your turn. Try solving problems 1 through 4 and determine if they're polynomial functions or not. Then match the graphs with the letters. So for example 1 says 6x to the 7th plus 3x to the 5th plus 2x divided by 3. First you need to discover or identify if it's a function, and if it is, we need to match it to the one on the right, to the graphs on the right. So try that for now and we'll take a look at it in class. So in part 2 of this, we're going to look at the end behavior of a graph. Now these should be very easy. All we're doing is we're looking at the end of the graph and we're trying to determine their behavior. So you'll notice in these examples, I've purposely blocked out the middle. Now if you look at some of these examples, example 1 in particular, it goes down and to the left and goes up and to the right. Now if we take a look at that function, you'll notice that it's to the third power. Now because it's to the third power, that means it's an odd graph. When it's an odd graph, it means these two arrows that we just drew, this red one and this red one, it means that these graphs, when it's an odd function, go in the opposite direction. Because it's a positive 6x cubed, if you look at their lines, it's almost like it's a positive line, positive straight line, that's going in the positive direction. Now let's take a look at the middle. What happens in the middle on end behavior doesn't matter because, like I said, we're only looking at the end behavior, the ends. Now if we look at example 2, while I'm drawing these arrows, take a guess, is it going to be an odd function or an even function? And if it is it a positive or negative one? So you'll notice here, opposite direction, that must mean it's an odd function. And because they're going in a positive direction, it should be a positive. So that's 7x to the 5th. That's an odd exponent, and it's positive, so it should be going in that direction. Again, the middle we don't care about. Example 3. You'll notice that this time it's an even function. And because it's an even function, that means the arrows should be going in the same direction. Because they're both going up, you'll notice that the x to the 4th is a positive x to the 4th. The stuff in the middle doesn't matter. If we take a look at example 4, you'll notice both going in the same direction. That means this thing is an even function. Because it's going downward, that means that the even exponent is positive. So it's negative. So you have negative x to the 4th because it's going downwards. So this is the important part. This is how we sketch and discover what these graphs look like. We find the zeros and the multiplicity of a function. Now, multiplicity of a function just refers to how many times this thing occurs. So let's take a look at this one. In example 1, the first thing we're going to want to do is solve for x. So because this is already factored, and we know we have the zero product property, we can type in x minus 5 equals 0. We can also type in x plus 4 equals 0. Now, because we have x plus 4 quantity squared, that means we have this with a multiplicity of 2. Multiplicity of 2 because it's squared, that means we have it twice. So when we solve both of them, we have x equals 5, and we have x equals negative 4, and sometimes you'll see dr for double root. That means it happens twice. Now, I'm going to show you the graph, and you'll notice that this is an odd function, looking at the end behavior, because it's going in the opposite direction. But if we look at the graph, let's see how the graph matches up with our roots, or our solutions. So you'll notice that it crosses the graph here at negative 4, and it crosses again at 5 right here. The interesting thing though is, how does the double root affect the graph? And you'll notice here that as we track it, it goes up to negative 4 and then it bounces right back down. But when we graphed it for 5, it just crossed right through it. So for the single root, it just crossed right through it. But for the double root, it bounced right back. Now when we do number 2, well, we're going to find our roots. So x minus 3 equals 0, which is x equals 3. And we do it for the next one, we have x plus 6 equals 0. But this one is a This one has multiplicity 3. Now when we have multiplicity 3, we find that this thing is x equals negative 6. So if a single root goes through the line and a double root bounces back, what does a triple root do? So when we do this, we find that this thing, right around negative 6, it kind of stays flat. So it goes down and it lays flat for a decent amount of time, and then it goes back down. And when we go through 3, it just crosses right through it. So that's how these graphs are affected. So you definitely want to write that down. Single roots cross right through the x-axis, double roots bounce, and triple roots lay flat. So in example 3, it's not in the zero product property, so we have to factor really quick. So we have x to the third power plus 4x squared plus 4x equals 0. And then we notice that they all have an x. So this is going to become x squared plus 4x plus 4 equals 0. When we factor this, we are going to get a funky number. Actually, no, we're not. We're going to get x minus 2, or x plus 2 times quantity x plus 2 equals 0. So you'll notice here we have x equals 0, we have x equals negative 2, and x equals negative 2. So notice we have x equals 0 again, and x equals negative 2 double rooted. So how does that affect our graph? Before I even show you the real one, we're going to graph it from scratch. Now, using our n behavior, because the degree is to the third power, we know automatically that these two things are going to go in the opposite direction. So what we could really do is just start with our n behavior. Again, it's the third power, that means opposite directions. So here we go, we have our graph. And then we have x equals 0, so I'm going to make a point there. And then we have negative 2 double rooted. So, starting from our n behavior, we're going to track that up. We're going to get to negative 2. Once we get to negative 2, we have to determine, does it bounce, does it lay flat, or does it go straight through? Because it's a double root, it bounces back down. And then we know at some point we have to go back up so we can end in that direction. So that's how we sketch a graph. When we look at the real one, it's not too far off, but it gives us a decent sketch of what it's going to look like. So now it's your turn. Try these 3 problems, first by finding the zeros of the polynomial, and then sketch the graph using n behavior and zeros, just like we did earlier. That's all for now. I'll see you guys next time.